Welcome back to Calculus 2 Online. I'd like to talk to you today a little bit about one of my favorite tests for series convergence, test called the alternating series test. We're going to start with an example. We've seen before that the series that is made up of the reciprocals of the positive integers, we call that the harmonic series, is divergent. Right? We've seen several arguments for why that might be the case. What I'd like to talk about today is what happens whenever we take the similar series, right? So still n equals 1 to infinity. We're still going to look at reciprocals of the positive integers, but we're going to alternate the signs. So let's see, we can indicate that I want my first term to be positive. So I think if we write the series like this, then what we've got is, well, it's going to be 1 over 1 minus 1 over 2 plus 1 over 3 minus 1 over 4, and so on. So it's the harmonic series, except with every other term being subtracted rather than added. So positive, negative, positive, negative, positive, negative, and so on. We're going to continue in that fashion. And we're going to ask, does this series converge? Well, we can get a sense of this by drawing a picture. So here's my picture. I'm going to plot the partial sums of this series on the real line. 0 over here is a reference point. First partial sum, of course, is 1, right? And then we're going to subtract half away from 1. So that's going to put us right about there. It's going to put us at 1/2 exactly. So this is 1 minus a half. Right, so that's the second partial sum. 1 minus a half plus a third. Let's see, a third is going to be about that distance right there. So tack that onto here. Maybe about this. 1 minus a half plus a third. And excuse me. We're going to continue in this fashion. So now I'm going to subtract a fourth. Let's see, a fourth is that distance right there away from there. So it looks like maybe there. So that's the fourth partial sum. It's getting inconvenient to write all the terms, so I'm just going to write S4 to mean the fourth partial sum. Add a fifth partial sum, subtract a sixth, and so on. And what it looks like is happening is that we're honing in on some number, right? We've got, so if I look at the second partial sum, the fourth partial sum, the sixth partial sum, and so on, let's see, so second partial sum, fourth partial sum, sixth partial sum is somewhere there someplace. We have this increasing sequence that doesn't seem to be getting as high as any of these terms up here, any of these partial sums up here. If I looked at the odd partial sums, the first one, the third one, the fifth one, right? The first one, the third one, the fifth one. I have this decreasing sequence of partial sums that seems to be honing in on this number right here. So it looks like looks like this series converges. And in fact, the answer is yes, it does. It converges, and converges to a rather surprising number. You might wonder what this is, and I can tell you right now, but we're not quite yet in a position to prove this. Turns out that this series converges to the natural log of 2. Surprise. So why is this working? Why is this happening? What's going on here? Well, first of all, let's define this type of a series right here. So a series for which every other term is positive and the other terms are negative is called an alternating series. So this is an example of an alternating series. And so specifically, we're going to define an alternating series like this. Let's if A1, A2, and so on are all positive, then the series A1 minus A2 plus A3 minus A4 and so on is called an alternating series. And so this is an example of an alternating series, but it's a very special one in as much as each term, right? I'm insisting that A1, A2, and so on all be positive, and then I'm going to alternate the signs in order to create my series. So, right, 1 over 1, 1 over 2, 1 over 3, 1 over 4 are all positive, and I'm alternating the signs to build my alternating series. This particular one has the additional property that A2 is less than A1, A3 is less than A2, A4 is less than A3, and so on. And that's exactly the sort of alternating series that turns out to be convergent. So let me state this as a theorem. So we'll go ahead and write this again. If A1, A2, and so on are all positive, and the corresponding sequence of terms is decreasing, with limit 0. Then A1 minus A2 plus A3 minus A4 and so on is convergent. And sometimes we call this the alternating series test for series convergence. Right, very nice result. It's clean, it's easy to use, and it's I think it's even somewhat intuitive, right? If we're always decreasing the terms, then whenever we look at every other partial sum, if we're looking at the even ones, we're going to get an increasing sequence. If we look at the odd ones, we're going to get a decreasing sequence, and they're going to all be trapping some number in between them. And the fact that we're insisting that the limit go to 0 means that this number that they're trapping in very, very small intervals, decreasingly small intervals. And so that forces the series to converge. And we're going to prove that a little bit more rigorously, but that's the basic idea of what's going on. Now, before going on, I'm going to ask you to see if you can remember what the mantra is for this chapter. Take a moment. Remember, it begins if the sequence of partial sums. Did you get it? All right, let's look back at it here. So mantra is that if the sequence of partial sums of a series converges, then the series converges. And we're going to use our mantra again to prove that alternating series with the characteristics that we've talked about, we're going to prove that such a series converges by employing our mantra. And we're also going to use, you'll recall, one of our main tools for sequence convergence is the bounded monotonic convergence theorem. And it says that if a sequence is both bounded and monotonic, then the sequence is convergent. So what we're going to show is that the sequence of partial sums of a series is both bounded and monotonic, right? So we're going to take an alternating series for which the individual terms decrease to 0, and we're going to prove that with such a sequence or such a series, the sequence of partial sums is both bounded and monotonic. But then, since the sequence of partial sums is bounded and monotonic and converges, we have that the series converges. So that's our plan. Let's erase the board and start again. So here it is. We're going to prove the alternating series test. So we'll start with a bunch of positive numbers. And let's see, what were some of the conditions? Well, we need for this sequence of positive numbers, haven't built the series yet, but we want the sequence of positive numbers to be decreasing. That's going to be important. And we want the limit of the terms to be 0. Now, you recall the limit of the terms is going to have to be 0 anyway if we're going to have a pair of the corresponding series being convergent, right? Our pair of convergence test, which is often called in standard textbooks the nth term test, but I like to call it the pair of convergence test. It reminds us about what it is it's saying. So we're set up here, and let's let Sn, let Sn denote the nth partial sum of the alternating series. Right, and let's see, so we're adding on the odd terms, subtracting off the even terms. So out here I have some an. Don't know if this is going to be positive or negative because I don't know whether n is even or odd. But in any case, we're going to let Sn denote the nth partial sum. And so let's look at a couple of partial sums that end with even terms. So, right, we might be talking about the second one, we might be talking about the fourth partial sum, and so on. And so I'll indicate an even partial sum by writing 2n, right? So if n is 1, this is 2. If n is 2, this is 4, and so on. So that's going to look like, well, a1 minus a2 plus dot dot. Going to have some a 2n minus 1, right? That would be an odd number minus a 2n, right? So that would be the 2nth partial sum of this series. And the next even number after 2n is 2n plus 2, right? It's going to look like a1 minus a2, and so on. Same terms we had before. With the addition of 2 more. All right, so there we go. Now, you may recall we pointed out that, let's bring back the old board. It looked like the even partial sum, so this would be the second partial sum. There's the fourth partial sum, and so on. It looks like the even partial sums are forming an increasing sequence. And I'd like to prove that. I'd like to verify that. And I can do that by looking at what happens if I take the 2n plus 2th partial sum and subtract the 2nth partial sum from it. Now, what I ought to get, if our observation was correct, whenever I take, say, S6 minus S4, I ought to get something that's positive. I ought to get something greater than 0. And that's what I want to prove. So, well, this is going to be, we have these two expressions written up here, these two partial sums written. Well, if I take the 2n plus second partial sum and I subtract from that the 2nth partial sum, Let's see. So let's see. 2nth partial sum. That's a1 minus a2, and so on. Right. So if I subtract this from that, all I'm going to be left with is a2n plus 1 minus a2n plus 2. Right. But recall that the terms of this series are forming a decreasing sequence. And so a2n plus 2 is a smaller number than a2n plus 1. So in fact, that is greater than 0, as we predicted it was going to be. So this partial sum is always going to be a larger number than that partial sum, which says that the even partial sums of the series a1 minus a2 plus a3 minus a4 and so on form an increasing sequence. Right? And furthermore, observe that those sequences are never going to get, well, they're certainly never going to get any larger than the very first term in the series. Never going to get any larger than the very first term in the series. And so that means that they're bounded. So moreover, this sequence is bounded. And so the sequence of even partial sums is both monotonic and bounded. Right? And therefore it converges. Right? A similar thing is true for the sequence of odd partial sums. And I'm going to leave that for you to do. So I'm going to ask that you show that the sequence of odd partial sums is also monotonic and bounded. Right? And so the even ones are converging to some number. The odd ones are converging to some number. And the fact that the terms themselves are heading to 0, well, that is going to imply that the difference between what the even partial sums are converging to and what the odd partial sums are converging to, right? The individual terms are getting close together. And since the individual terms are getting close together, these guys must be converging to the same number. And that's a bit of a hand-waving proof there of the alternating series test. Another very nice feature of the alternating series test is the ability to easily approximate how good a particular partial sum is at approximating the value of the entire series. And let's go back to the earlier example that we had seen, the alternating harmonic series, to see if we can understand why that might be the case. So let's go back to this slide. So notice now this second partial sum, for example. Well, first of all, it is to the left. It is less than the sum of the series, log 2. Well, because we'd subtracted, the last thing we did was subtracted a term, right? So the even terms are all going to be, the even partial sums are all going to be less than log 2. The odd partial sums are all going to be greater. But notice what happens whenever we go from this second partial sum to the third one, right? Here's our second partial sum. Here's the third partial sum. We got to the third partial sum by adding a third. But when we did that, we skipped over log 2. We skipped over the sum of the series as we went from the second partial sum to the third partial sum. And notice that this happened again as we proceeded from the third partial sum to the fourth. Whenever we proceeded from the third partial sum, which is greater than the sum of the series because we added as our most recent operation, we went from something that was greater to something that was less. We jumped over the sum of the series whenever we tacked on the next term, the negative 1/4. So what's that telling us? Well, what it's telling us is that 1 minus a half approximates the sum of the series to within a third of its actual value. The third partial sum approximates the sum of the series to within a fourth of its actual value. And what's important here is that a fourth is the fourth term of the series. So the second partial sum approximates the series to within the third term, 1/3. The third partial sum approximates the sum of the series to within the value of the fourth term, and so on. So let's state that a little bit more concretely. So if A1 minus A2 plus A3 and so on, minus A4, is a convergent alternating series, then the nth partial sum, that's A1 minus A2 plus A3 and so on, up to, and I don't know if I'm adding or subtracting here at the end, but the nth partial sum is within an plus 1 of the sum of the entire series. right? And so in our example, if I wanted to look at the, say, the 100th partial sum, let's see, the 100th partial sum, I'm always adding on the odd terms, I'm subtracting off the even ones. And so I know that the 100th partial sum, let's see, in our example, that's going to be 1 over 1 minus 1 over 2, and so on, plus 1 over 99 minus 1 over 100, is within 1 over 101 away from the sum of the series. So even if I didn't know what the series added up to, I would be able to evaluate this 100th partial sum and say that even though I don't know what the series adds up to, I know that it's going to be, the sum of the series is going to be no more than this far away from whatever that sum happened to be. So in this case, log 2. Let's look at that another way. So I'm going to take us to new screen here. Perhaps you are familiar with Wolfram Alpha. It's a wonderful tool. You have access to it. Just go to it. And let's experiment a little bit. So what I have here is I'm asking Wolfram Alpha to sum the series that we're interested in, the alternating harmonic series. Let's see, well, from 1 to infinity, just to kind of confirm. And we have that that's equal to log 2. Yeah, there it is. And so let's see, log 2 is approximately 0.69315 approximately. And if I wanted to just add up the first 100 terms, now take another close look here. 6931, right? Memorize those numbers for a moment. Might want to write them down. And now I'm just going to add up the first 100 terms. And remember, so this is the even partial sums are all going to be less because subtracting is the most recent operation we're going to do. So we're going to get something less. And let's see by how much. So what we got was 0.68817. Well, if you subtract 0.69315, that was approximately log 2, take that minus 0.68817, you get something that is less than 1 over 101. Give it a shot. Try it out. And so that's confirming what we just stated here a moment ago. So let's go back to our screen. So I had jotted these down. This was log 2. This was 1 over 1 minus up through right, and we got something a little bit less as we expected to. And in fact, if we actually subtracted this from that, we're going to get something that is smaller than 1 over 101. Let's see, what do we actually get? Looks like we get let's see, this is going to be a 0. And well, let's just go from this side. What do we get? 8, 9, 6, 0, right? And this number is less than 1 over 101, which was the 101st term of the series, so the n plus first term of the series. Now let's finish up with an interesting example. So let's consider the series 1 minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial and so on. All right, so I guess I could shorthand that as negative 1 to the n plus 1 over n factorial, as n ranges from 1 to infinity. So let's see. Is this an alternating series? Well, yes, right? 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial are all positive numbers. And those positive numbers are forming a decreasing sequence. And the series is formed by alternating the signs of the terms of that series. And those terms have a limit of 0. The sequence of terms goes to 0. So it meets all of the conditions of the alternating series test. So we know that this is going to converge. Right, so this meets the conditions of the alternating series test. And therefore, the series converges. Right. Moreover, we could estimate to what value this converges. Factorials get large rather quickly, and so these reciprocals of factorials are getting small very quickly. Let's estimate. So tell you what, let's go to go back to Wolfram Alpha again, and let's evaluate these. Let's see. So if I went all the way to 100, that's going to get, that's going to give me a little bit too much information right now. Let's just go up to, we'll go up to 10. Right. Actually, let's start by going up to 5. All right. So if we add up those first 5 terms of this series, we get 19 over 30. So we get approximately 0.63333 repeating. You might want to jot that down. We do not at this time know to what the series converges, but what we can say for sure is that whatever the sum is no more than 1 over 6 factorial away from the value. Now, also want to ask, is what we're looking at, 0.63333 and so on, is that going to be greater or less than the sum of the series? Well, we went up to an odd number, and all of our odd partial sums, the last operation we did was add. And so this is going to have to be greater than the value of the sum of the series. And it's going to be within 1 over 6 factorial, which happens to be 1 over 720 away from the actual value. And so we could say that we know that, let's see, 0.63 are going to be at least the first two numbers in the sum of the series, because 1 over 720 is certainly less than 1/100th. So 0.63 going up to the 100th spot, we're going to be correct up at least till that. If we went to the 10th partial sum, so I get 0.632125 and so on. This is going to be, let's see, can you determine, is this going to be less than or greater than the sum of the series? Well, we're looking at the 10th partial sum, and the 10th partial sums are all smaller because the most recent operation we did in the series was subtract. So this is going to be less, and it's going to be within 1 over 11 factorial away from the sum of the series. So I urge you to check that out. I urge you to verify that. And as it turns out, and this is going to be just a little bit surprising, as it turns out, this series, in fact, adds up to 1 minus 1 over e. And so knowing that will help you to verify that the 10th partial sum is within 1 over 11 factorial away from the sum of the series, within 1 over 11 factorial away from this number right here.
And that concludes our discussion of the alternating series test. Join us next time whenever we meet again to discuss absolute and conditional convergence. Until then, stay healthy, and I look forward to seeing you. Take care.